This is Statistics 243 at UC Berkeley for Monday, October 6th. Okay, so let's go ahead and get started. So when we left off last time, we were talking about object-oriented programming, and we had walked through some of the details of how the S3 system is handled in R. So I wanted to talk about this little problem that I told you about at the end of class last time, and talk that through. And then I'll switch and I'll say a little bit about something called computing on the language, which is basically when you use code to itself create and evaluate more code. And I'll talk about how you can do some of that in R. And then we'll switch over and start in on Unit 7, which is on what does it mean to work with numbers on a computer and what are some of the problems that you can run into when you're doing arithmetic on a computer as opposed to arithmetic by hand or mathematically. Okay, so here's the goal of the problem. I'm a really lazy guy. I want to just be able to hit Q at the command prompt and have R exit without me doing it, without me having to answer any questions or do anything else. Okay, so I'm going to turn to my panel. Is Bennett here? No? Okay. Chris. Okay, so when I type Q, what is R actually going to do?
It's going to figure out the class of that object and call a print function for that class.
Okay, so let's start there. So I'm going to type Q, and what it's going to do is it's going to, anytime you type the name of an object and then hit enter, it's going to go say, oh, you want me to print something. I'm going to call a print function. It's first going to call the generic print function, which we could actually look at just to recap here. Okay, so this is the generic print function. It does this use method, and then it's going to go look for a print method that's appropriate for the class of the object that you called it on. So at the moment, Q probably doesn't exist, right? So what's going to happen? It's just going to be an error. Right? Okay, so suppose we actually had Q existing, and now we say Q. Well, of course, it's just going to print out 7 as opposed to printing out what we wanted to print out. Okay, so sorry. Remind me what was the last thing you said? It's going to look for a print method,
and then call it on that object.
Okay.
And then you want to redefine that.
So this is going to call, so whatever type of object Q is, it's going to call the print method that's appropriate for that object. So in this case, with it 7, it's probably, I don't think there is necessarily a print.numeric. There's probably a print.default that it will call. So we could look and see what print.default does. Okay, so print.default does all of this processing to then print out whatever it's supposed to print out. So actually we could try print.default directly on Q and see if it seems like it works. So it may very well be that it's just calling this default function. Okay, so I don't want the generic printing behavior. I want something else to happen when I type Q. Right? So is Lindsay here? No? Mike? Okay, so following up with what Chris was saying, what do you think we need to now do? Okay, so I want a new specific method. Okay, and what kind of object do I want Q itself to be? Okay, so if Q were a function, then it won't quite satisfy the rules of what I'm trying to do here. Because if Q is a function, I'm going to have to call it like that, right? So what do I want Q to be? Anybody want to jump in and help? A list? Okay, so we want Q to be some sort of object. Okay, and if I'm going to make a print function that corresponds to that kind of object, what would I do? What do I have to do at this point? Plus? Oh, class. Okay. So let's say that Q is a list, and let's just make it an empty list. Okay. And so now what do you want me to do in terms of a class? Somebody else? What's that? Yep, so I want it to be a new class. So I'm going to say that the class of Q is, and now let's give it a name, quit object or something. Okay, so I'm going to say, since this is S3, it's very informal. I can just make a new class by defining this object to be of a particular class where I just give it a new character, where I just assign a character string as the name. If we're using S4 classes, we'd have to be more formal about this. But okay, so now I've got this. Now I've got Q. It's a class of type quit object. Now if I type Q, it just returns back, oh, this is a list, and this. So this is now still just calling the default print method on the object Q. So now what do I need to do? Yeah.
You want to define a function on print.quitObject.
Right. So now I need to define the specific method print.quitObject, which is going to be a function. It's going to have to take. I don't know if it has to be called obj, but that's what I tend to use. We could look and see what. I guess the print default just calls it x, so we could just call it x to be consistent with that. Okay, and now what I want this function to do is what I had set up here when I said what our goal was. Our goal is that we want this thing to then carry out this operation, because this is the operation that's going to cause R to quit without asking me any more questions or doing anything else. Okay, so let me just throw that into the print function. Where am I here? Okay. So it's just a one-liner. I actually don't need the squiggly brackets, but it doesn't hurt to have them here. Okay, so now I've got print. So now I have a specific method for this kind of object. I have the Q object, which is of this class. So I should just be able to hit Q and have this all work. Indeed.
I'm wondering if there's a difference in RStudio and
Yeah, so I'm going to fall back on my usual excuse, which is RStudio is doing some weird things here.
I found a message where it's talking about how RStudio assigns a fatal error.
Okay.
Cases inside the function.
If you put quit inside, or if you put the quit function, which is Q, inside another function.
So I couldn't figure out if it was unique to RStudio.
Okay. Yeah, so I think it probably because RStudio is wrapping a bunch of stuff, something more complicated is going on here. But this should work if I do this in R, because in fact I actually have this Q defined and this quit object defined in my R profile, because I'm the one who's being lazy here and I want to avoid I want to be able to just type Q. So okay, this is my quit object, and then I have print.quit object gets a function of x. And what does it do? It just quits with save equals no. Okay, so now this should work, and indeed it does. So you can see all it did was it just returned me back to the Unix prompt.
And then what is passed to the x function?
So what happens when this all gets evaluated and interpreted by the R interpreter is, okay, we type Q, it goes and calls print on Q, with Q as the incoming object. So now if we look at the print method, Q becomes x in the frame of this function. X, it's a little bit hard to know exactly what happens here, but basically the x, which is Q, gets passed on to print.quit object, and our print.quit object takes that. So it still has this list coming in here. It doesn't actually get used. It just evaluates this, and then R quits, and all of this becomes a moot point. Okay. Any questions about that example? So I like that because it's something that it's sort of a cute thing that I found at some point and realized that I could save me a little bit of typing every time I want to close R, and also I think it nicely illustrates some of the object-oriented stuff as well. Okay. Any questions or comments? Obviously, it doesn't seem to work in RStudio, and if we wanted, we could potentially go investigate that a little bit further. But okay, so let me. So I'll just say a couple brief things about S4 and reference classes. So S4, it's somewhat different syntax to work with these things, but in some ways it's not so conceptually different from what we've just talked about in terms of S3. And so if you look through this on your own, you should be able to pick that up pretty quickly. One thing to know is you have to get at the component members, not with a dollar sign as we did with S3, but with an @ symbol in S4. But there's the same idea of we can say what are the we define, in this case we have to formally define what are the components of an object, and we have to define where all the methods associated with an object or a class. And in general, we often want to write a function that is called the constructor, which will create an object in our class. And we can do that. We can do that in S3. We do that in S4 as well. I don't think I want to say too much more about it. Again, we have to define generic and specific methods, so there's a syntax for doing that. And in terms of reference classes, things are not so different. Again, the syntax differs, but again, if we want to create a class, we call this function setRefClass. We say what the fields are. These are components that contain the member information. And then we say what the methods are, the functions that operate on the objects in our class. And we can define, for example, define a constructor and call it initialize. That's the standard name for the constructor function. And then we could define other functions that we choose, other methods. And then we can use it, in this case the reference classes, we can use it in this sort of way where we call new, when we call new it invokes that initializer, that constructor, and whenever we want to call one of our methods, we do it with the name of our object and then $, and then the method that we want to use. So again, it's just sort of variations on syntax, but the big picture ideas are the same. And the nice thing about reference classes is whenever you work with reference classes, unlike S3 and S4, it's not making new copies of the objects all the time. It's basically when you call a method that would modify an element of the object, when it's a reference class, it's going to modify it in place without making a copy of the whole object. So this is one way of doing pass by reference instead of pass by value if you work with these reference classes. So I think that's all I want to say about that. I know I've sort of jumped through that quite quickly. Are there any questions? Yeah, JR.
Does this representation thing is set like what kind of, let's say for their thing, you have name is character, age is numeric. What if you have another list in there, and then can you actually set the representation of components within the list?
Oh, that's an interesting question. So you're saying, okay, you want to have a list be a component of one of these classes,
Yeah.
and then you want inside the list, you want to say, oh, the list has. Yeah, I don't think that's going to be possible because the whole idea of these classes is it's with a class that we say what are the specific components and what kind of components are there. If you embed a list in there, it's just like working with a regular list, and lists don't have any structure to them. You can put whatever you want into a list.
Or can you set another class?
Yeah, so you could nest. You could have another class so you could have your outer class contain an object of another kind of class as the component within the outer class, and that object that's nested within it would have carefully defined components. So that's how you would put all this structure into a nested sort of situation. Other questions? So you guys will get some chance to practice with these on one of the problems in the problem set. As I mentioned in the problem set, for any of you who've already worked with S3 classes a fair amount, go ahead and try your hand at either S4 or the reference classes just to try something different. But if you haven't worked with them, then it's up to you whichever one you happen to want to try and play around with. Okay, and I'll just make a brief note. I have a little bit of stuff in here if you wanted to actually use an environment as a way to basically pass things by reference as opposed to passing by value, because basically environments are ways to sort of work with pointers in R. And basically what reference classes are is basically a wrapper around this sort of usage that I have as examples here. So if you're interested, you could take a look at that example. But this functionality is basically superseded by reference classes, so it's really only important if you're sort of intrigued by it. Okay, so the last thing I want to say talk about in this unit is a little bit about this idea of computing on the language. And it's basically a sort of meta idea that you can use R, since R is so flexible and allows you to basically work with elements of the R language as objects. You can basically use R to write R code and use R to basically evaluate R code. So I could use R to create strings of characters that are basically legitimate R code, and then I could take those strings of characters, turn them into actual language objects that are legitimate R code, and then evaluate that newly created code. So this can come in handy if you sort of get into more complicated programming. And so I don't want to go through all this in a great deal of detail because it may not be something that you encounter all that much. But let me just show you a couple examples just to give you a feel for this. So the first thing is that, and I think I'm actually just going to switch over to RStudio. I don't think I'm going to gain much from being in the PDF. So where are we here? Oops, come on. Okay. Okay, so the idea is if I want R to treat a piece of syntax of an R statement like this as language instead of actually going and evaluating the code and returning the results, I will take the code that I want R to treat as language and wrap it inside a function called quote. And what quote does is say, don't treat this as code to be evaluated. Treat it as code that you're going to keep as an object and be able to pass around and work with. And so the result of doing that is this object is, there are various kinds of, various classes or types of objects that basically are basically relevant for when you're working with actual R language objects. And I guess I do need to go back to the PDF. I have a little table here that says what they are. And basically they're things, most of them are of type language. That's sort of the fundamental way that they're stored in the underlying C code. But their classes are basically things like this. And so they can either be expressions, or if they're just function calls, they're called calls. If it's an if or a for statement, they're actually sort of special kinds of calls. So if you ever see that the class is something like this, you know you're working with a language object. And in this case, the class of the if statement is actually of class if. And so working with these objects are sort of stored in a way that's not all that helpful to us, except we can take a language object and convert it into a list. And that actually allows us to sort of see what's going on and how R basically parses the language that we're giving it, the code that we're giving it. So if I say as.list of object, what it does is it prints out the result in a sort of helpful way, which is basically it's sort of like a list. It's got these 4 components. And you can sort of see how it corresponds to what this is. The first thing is generally going to be the basic call, the basic kind of function or operation that is being carried out. So in this case it's if, and you'll notice the back ticks to sort of indicate that it's code. And now if you look at this, you can sort of look at this, and if you stare at it for a little bit, you'll see this idea that I've sort of harped on a couple times in the last few classes, which is basically any operation in R is a function, even if sometimes it doesn't look quite like it's a function. So an if statement is also a function. And if you look at an if statement, you can sort of think about what the arguments of that if function are. Well, it's going to be the condition, and then what happens if it's true, and what happens if it's false. So the first argument is x greater than 1. Second argument is what happens if it's true. The third one is what happens if it's false. So that's where the orange and the apple are coming from. Okay. So it's actually really sort of an if-else statement, because the else is sort of embedded in there as the last argument of this function. Let's see. And I could actually sort of like what I did with the plus function, I could actually write an if statement in this sort of funny way where I actually explicitly write it as a function, where I'm calling the if function with these 3 arguments. And the result of that is going to be identical to what I just created using sort of the more standard way of writing out an if statement. Okay, questions at this point? So there's a whole bunch of stuff in here about sort of the details of what kinds of objects are created when I do when I pass in different kinds of code to the quote function, or the expression function is basically very similar to the quote function. Either way, you can pass in code and it'll basically hold on to that code as a language object instead of actually evaluating the code. So I don't want to go all that deep. I don't really want to go into the details of that. I thought what I would do is just show you one example that I think illustrates this a little bit more. And then we'll basically leave it at that. Okay, so I'm going to do it. I'm going to do it with this more complicated expression. And what's basically happening when we call quote is basically something similar to what happens when R takes a block of code of any length and has to then interpret it and run the code. Basically what has to happen is the R interpreter gets fed in this block of code, and it has to parse that code and put it into a sequence of statements that it can then execute and operate on. But if you think about what has to happen when you, even just with a single line of code that's sort of complicated like this, is R has to sort of figure out what are the operations that have to happen in what order. So in order to do this, you can say, well, okay, in order to do the mean, I need to basically deal with the first argument, and I needed to deal with the second argument as well. We've sort of talked about promises and the point at which these things would get evaluated. But sort of another perspective on thinking about what has to happen here is, if it's going to evaluate the mean of let's see. If it's going to evaluate this mean, it first has to go in and realize, oh, I'm going to have to do a plus. And in order to do that, I'm going to have to do this R norm, and I'm going to have to do this concatenate statement. So you can sort of think of what R has to do, and this is what interpreters in general have to do, is they basically create a tree of operations, and then they can basically work their way up from the bottom of the tree to carry out the operations. So if we think about what the tree would look like in this case, we've sort of got mean at the top, and then actually mean doesn't really have two things coming off of it. It really just has one thing coming off of it. Because if you sort of think about what has to happen here, the next thing in precedence here is basically the plus, because the mean is getting evaluated on the output of the plus. So then there's a plus. And there are two arguments to the plus, which is the C of 12, 13, 15, and the R norm. So there's a C function, and then there's an R norm function. And then if you think about the arguments to those functions, well, the C function is getting in, what did I say up here? A 12, and a 13, and a 15, and the R norm is getting in a 3, and of course it's also going to have some default arguments, the 0 and the 1 for the standard normal. So are there any questions about what I've written out here? So basically, when R is trying to interpret that code, it basically creates this. And once it's created this tree, if it wants to evaluate that code, it can basically work from the bottom up. It can evaluate the concatenate function, produce the result of that, evaluate R norm, produce the result of that, take those two things and add them together by the plus function, and then pass the result of that into mean. So you sort of need to work in this sort of fashion. And if we actually look at this and look at what this looks like, we can see that basically when we print, it's not a list, but it's sort of in a form that's like a list. So if we do as.list, it'll sort of show it to us in a helpful format. So if we say as.list of E3, we see indeed there's the mean, and then the second piece, which is the argument of mean, is this, which is basically the whole thing that gets passed in. But now if we say, well, what's in that second component of E3? Oh, well, that's interesting. That indeed is the plus operation with the two things that get fed into the plus operation. So that is this piece of what I wrote out there. And I can continue burrowing into this sort of nested set of things and say, well, okay, what about this third thing? What does that look like if I burrow in and look at the parse tree for that third piece? And it's what you would expect it to look like. It's now R norm and 3. And now we've gotten to the bottom, and there's nothing left that needs to get evaluated. Now it's just a value that's getting input into a known function. Yeah, Eugene?
Is this list representation created to default as list, or is it created implicitly and then just displayed in the run?
E3 is a call object, which is one of these language objects. I don't know exactly how it's stored. I mean, it's stored as some sort of C structure. And the as.list is taking, I think what it's doing is taking that basically that C structure and sort of its R interface to it, and then printing it out in a way that makes it look like a list. So I think it's happening essentially on the fly. Other questions? Yeah, Ray.
So far, all the questions like embedded functions. All the functions are embedded. So what if we have like self-defined functions if you want to use a code? The same.
Yeah, so I mean, there's nothing sort of magical about. I mean, I could have done my fun is a function of x, and it does whatever, print of x. And if I had instead defined E3 to be my fun of whatever, this should look the same basically. Okay, so it's got my fun of 7 there, and then if I do, oops, what did I do wrong there? E3 of 3, oh, of 2, okay, sorry. Okay, so these, once you've defined a function, it's really not that much different than any already defined function in R. Yeah. Other questions? So it's actually, I could actually do things like I could actually go into the object E3 and actually change some of the elements in there and then evaluate it, and I would actually get the result. The result would be sort of the result of evaluating the code as I changed it instead of as I'd actually put it in there, instead of as I'd actually originally defined the code. And I have an example of that here that I don't think I'll take the time to go into. But all of this stuff can come in handy, and there are times in which you sort of want to dynamically generate code, and this is the sort of functionality that would allow you to do it. The other thing I will mention is you can go back and forth between character strings and R code that you can evaluate. And basically, if you have I defined an out here? Yeah. Let me define a language object out that just has y gets 3. That's the code that's in there. If I want to create text as a result of that, I can run the dparse function. And so out is y gets 3, but code text is basically a character string version of that. And if I want to go the other direction to basically create code from just strings, from character strings, I can run a function called parse, and that'll go from the string to the code. And so if I typed parsed code here, this is now in the form. It's a little bit different than it looked before. It's sort of treated as an expression for reasons that I don't think are worth getting into. But basically, I could evaluate this as R code as well. And I could do it as, let's see if there's a y at the moment. So there is no y at the moment. If I do eval on the result of running parse, and now I look for y, it says it is indeed 3. So it went ahead and evaluated that code. So this is the sort of thing where what you might do is basically write some code as character strings, use parse to convert it into a language object, and then use eval to actually evaluate the code, to actually run the code. Okay, so I think that's all I want to say about that. I just wanted to sort of give you a bit of a flavor of that so you knew that this stuff existed, and it may come in handy for some possibly small number of you, but I would guess at some point at least a few of you would make use of some of this kind of functionality. Any questions at this point? Yeah, Jared.
An example of how quote could be useful.
How quote could be useful?
Yeah.
So if I for some reason wanted to basically create a language object and then basically pass it around and use it at some point later in the processing, there's no way to do that unless I use the function quote. Because if I try to pass y gets 3 into some function, the result of that is going to be doing the evaluation of y getting 3. The only way to be able to pass it around as language is to use quote, and then to pass around the result of that, in this case out, to some other function. So if I did want to sort of be operating in a way where I was sort of passing stuff around and then doing stuff to it later on, I need to use quote.
Is that good practice though, to be passing around language?
Yeah, it can be. In certain cases, it can be quite helpful. There are cases where we're in projects I'm working on where we're basically constructing functions on the fly, and the way we do that is we basically write character strings. We convert the character strings into a language object, and then we make the body of a function be that language object. And then we basically, on the fly, also define what the arguments are, and so we basically construct a function, sort of from its component pieces. Other questions? Okay, so that concludes Unit 6, and I'm going to switch over to Unit 7. So as I mentioned in the announcement, at this point we're starting to shift away from really focusing on R as sort of R itself, and we're really just using R because we need a language to be able to illustrate concepts in. To some extent we've already been doing that, because a lot of things we've been talking about are things that would be relevant if you were programming in Python or MATLAB or C or any of these other languages. And so it's not like we're sort of learning a lot of things about R, but a lot of the things that we're learning are ideas that would carry over to other languages. But for most of what we're going to do in the rest of the semester, we really are learning about concepts, and we need a language to be able to illustrate things, and so we're using R to illustrate these things. Okay, so the sorts of things we're going to do in this unit are we're going to try and get to the point of understanding some about how numbers are stored on a computer, how they're stored in memory, and the implications of how they're stored in memory for how computations are done and what are safe and not safe things to do in terms of computations. So some of the sorts of things we're going to be looking at is, when is it safe to compare two numbers and expect them to be exactly the same versus approximately equal to each other? When is it safe to be doing arithmetic on two different numbers and expect that the answer is going to be reasonably accurate versus not being reasonably accurate? And there are going to be cases where you can go pretty far wrong by not sort of understanding how this all works at a more fundamental level. That being said, we're not going to sort of dive incredibly deeply into exactly how a computer does arithmetic with at its sort of most gory level of detail. But the idea is to understand enough to basically be aware of what some of the dangers are. Okay, so we have to start by thinking about bits and bytes. So you can think of a computer as basically just operating lots and lots of switches. There are zeros and ones. So this is that's what a bit is. It's just a 0 or a 1. And when we've been talking about things like how many megabytes does an object take up, what we're basically talking about is the fact that 8 bits make up a byte. And we've already talked about the idea that any real number in general is going to be stored as 8 bytes. So if we have 8 bits per byte and 8 bytes per real number, we're taking up 64 bits for any given real number that's stored on the machine. And so you really can think of any real number as just a sequence of 64 bits, where each of these things is a 0 or a 1, and they're put into this array of 64 bits in a particularly structured way, so that when the computer then needs to do something with this, it's able to operate on these bits in a way that makes sense to do the kinds of calculations that you need to do with the number at hand. Okay, so before dealing with real values with floating points is much more complicated than certain other things like integers. So let's first start by talking a little bit about some things that are a little bit less complicated. So when we're talking about ASCII characters, there are 128 different ASCII characters. And so if you think about storing, being able to store an ASCII character, we basically need 7 bits to store an ASCII character, because 2 to the 7th is 128. So with 7 bits, we can store 128 different values in there. Everything from 0000 to 00001 to 00010 to 0011, just enumerating all the possible combinations of zeros and ones. So I don't actually know the history of this, of why there are not 256 ASCII characters, because if you think about the idea that I've talked about working in units of 8 things, it might make some sense that there would be 256 of these, but for some reason only 7 bits are used to store characters. Okay, so if we're thinking about writing out, if we wanted to store an ASCII character, we could think about storing it as 7 bits. So here's our 1, 2, 3, 4, 5, 6, 7. I think we really do want to have 8 in there. Okay, so this is stored as some zeros and ones, and maybe this is the character lowercase z. I don't actually know what it is. And so if we wanted to, if we're thinking about writing out a word, then we would just need to have a bunch of these 7-bit values, and that would then allow us to work with an entire string. One thing that we'll often see, and we've already seen it in terms of memory addresses, is we've seen that storing things are generally written as base 16, because it's a lot easier to write base 16 than to write out all of these zeros and ones. So the idea is that if I have, let's see. So if I had a full 8 bits, so that's going to be 256 values, so that's a byte. I could either write that out as 8 zeros and ones, or I could equivalently write that out in terms of base 16 as 2 values to take the place of that. Okay, so that's why we would have something like 3e. So we would basically be taking the first 4 zeros and ones and interpreting that as a base 16 number between 0 and f. And then we'd be taking the second set of 4 zeros and ones and interpreting that as a base 16 number between 0 and f. So this would get replaced by, I'm going to be able to do this in my head, but this would get replaced by whatever the base 16 value was here, and we'd get 2 digits that are in base 16. Okay, so then just this comment of, we talk about file formats a lot. Well, what's a file format? Well, it's basically just, if you think of writing out the bits, if you think of the bits in a file as just being, well, the bits in a file are just zeros and ones, it's just basically how the computer interprets that long string of zeros and ones. How does it break it up into meaningful units, and then how does it interpret what the zeros and ones are? Okay, so let's think about integers. So suppose that I had, suppose I was storing integers as 2 bytes. So if I have 2 bytes, that means I have 16 bits. So here are the 2 different bytes. So if I think about the number of different unique possibilities for filling in these with zeros and ones, that's just 2 to the 16th possible different values. And so if I were storing non-negative integers, I can store anywhere from 0 up to 2 to the 16th minus 1, which would be 65,535. So if I were designing a computer and I were storing integers using 2 bytes, then the largest valued integer I could store would be 65,536. And if I tried to do something, use a value bigger than that, something would go wrong. So I presume that my computer would give me back an error of some sort. Okay, so of course, another thing that we need, so in general we'd want to be able to work with numbers that are bigger than this, of course. And we'd also want to be able to work with negative numbers. And so if we're going to take, instead of doing 0 to the 216th minus 1, we're going to put half on the positive side and half on the negative side. So we're going to end up being able to store things like with 2 bytes, we can store anywhere from minus 32,000 up through positive 32,000. And if we tried to use a number that was bigger than the largest possible number or smaller, larger in magnitude negative or larger in magnitude smaller, we would have what's called an overflow. Basically, we've got a number that's too big in terms of the way that we're storing numbers on the machine. Okay, so questions at this point? Okay, so let's actually see this in action. So actually, R is actually using, because it's just basically running C in the background, on most modern machines, integers are stored as 4 bytes instead of 2 bytes. So we can store 2 to the 32nd unique different values. And so if we look at this here, so I'm going to force A to be an integer in this case. So I can either do that by converting this number to an integer, because it would usually be stored as a numeric, as a real value, for reasons that we'll talk about in a little while. Or I could use this syntax here where I tap on a capital L, which stands for long, which is sort of an old style terminology for an integer, long integer. So if I store this value a as an integer, I can indeed store a number that's this large as an integer. That's sort of not too surprising because if I think about 2 to the 31, so I can store 2 to the 32 unique different values, and I'm going to put half of those in positive and half of them in negative. So 2 to the 31 should be about as big a number as I can store as an integer. And this is much smaller than that. So that's okay. But now if I try and multiply a times a, it says, nope, that's not possible. Okay. So it gives them back an NA. So that's what happens when R goes back to C, tries to do the computation, and again, it realizes it can't actually work with a number that's as big as the resulting product. And it gives the warning message is much more informative than just that I got an NA. It says in this operation, the NAs were produced by integer overflow. So this idea of overflow is you've done a calculation or just tried to assign a value in that's too large for the amount of storage that's allocated for integers. Okay, so if we think about objects in R, we can think about and see whether they actually correspond to this idea that I've been talking about, that integers are stored as 4 bytes per integer, real values are stored as 8 bytes per integer, and we could look and try and get a sense of what's happening with character strings as well. Let me just make sure I'm not forgetting something here. Yeah. Okay, so I'm going to create something I'm call a double vec, and basically real values are called doubles on computers usually, and what it stands for is double precision floating point. We'll talk about why it's called a floating point in a little bit, and we'll talk about why it's called double precision. But whenever you see double or hear me say double, what I just mean is some real value, okay? Some possibly decimal valued number. And I'm also going to create a vector of integers. The colon operator by default returns back integers as opposed to numerics, as opposed to real values. And I'm also going to create a character vector as well. So all of these are 100,000 long. Okay. So we would expect that the double vec is going to take 100,000 times 8 bytes, so 800,000 bytes. We can verify that's true. Yep. This is probably the 40 bytes here. The 40 extra bytes is probably the overhead that's involved in the meta information about the vector, like how long it is and things like that we've sort of talked about a little bit. And we should be able to verify here that indeed R is working with 4 bytes per vector. So 400,000 divided by 100,000 is just 4. Okay, so that just sort of verifies what I've been saying. And I think it's sort of interesting to look at the character vector. So there's this particular character vector, which is 100,000 long, and each one of these is letters is just the letters A through Z. So this is just a random sample of the letters A through Z. So it happens to be those 5 particular letters as the first 5. So let's pause and think about what R has to deal with when it's storing a character vector like this. So in this particular case, I'm just storing 100,000 different individual characters. So maybe what R could do is it could just store those continuously in memory. So what was it? I had an X, and then a G, and then a J. And let's ignore this bit about the fact that I said, oh, ASCII characters are in 7 bits as opposed to 8 bits. Or ignore that complication and just assume that R is going to store any character as 8 bits, as a single byte. So I've got got these values here, and suppose this is 0s and 1s that translate into X, and this is 0s and 1s that translates into G, and so on and so forth. And suppose I hypothesize to you guys that this is how R stores a character vector. It just stores it continuously in memory. Maybe I shouldn't have. Let's assume there's no space here. This is just continuous bits in memory. Why won't that work? So let me phrase the question a little bit differently. what else could I have, say, here instead of G as an element of my character vector? What's that? I could have Q, right? So I could have any single letter, but what else could I have? What's a
Or
double?
anything that's not a letter.
Okay,
Just a
so
character.
this could be replaced by the complete works of William Shakespeare, right? This could be an incredibly long character string that starts with whatever Hamlet starts with and ends with whatever a Midsummer Night's Dream ends with, and is millions or billions of characters long, right? So I sort of set it up here so that these could be taken up could make up the same amount of memory for each one of these. But if I now go in there and say, oh, you know what? Instead of having G there, I'm going to replace that. I'm going to make a copy of this for the moment because I want to come back to that original char back in a second. So now I'm going to say, well, what if charvec of 2 is blah 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 blah. Oh wait, sorry, that's not what I meant to do. Charvec of 2 is. Okay, so now it's pretty clear that I can't just substitute this in here into my 8 bits. There's no way it would fit. Okay, so what else could R do? So think pointers. What's that? Aurelian?
Point off to the next.
Have a what?
After the first character, point off to the next character where it's stored.
Okay, so what we could so what it could be is instead of storing stuff like this, it could be that the first element basically points off to where the X is actually stored. And then this points off to wherever, well, it was originally a G, but now it's become that whole gobbledygook. That it could point off to, A, B, C, E, X, Y, whatever it is. And this could point off to somewhere else. So what may very well happen is you could end up you could basically have the pointers stored contiguously in memory, but then because these things the things that are making up the character vector are arbitrarily long, those presumably have to be stored somewhere else. And if we look at, we can go back to our friend of using the inspect function and see what it says, and that's actually quite helpful. I actually didn't know this until a year or two ago when I started wondering about this in reaction to some of these kinds of discussions in class. So it says the overall object is one of these string S expressions, and it says that's located at this place in memory, and it says indeed it's 100,000 long. But then it also has this other information, and it turns out there's something different, something that's distinct between a string S expression and a char S expression. And it says, oh, indeed, these are the first five elements that we've already seen, the X, G, J, O, X. Anything else jump out at you here?
Location address.
So the location address here is different than here, which makes sense if that's actually how it's done. I don't actually know for sure that that's how it's done, but based on some evidence like this, I suspect that that's what's going on. So this is presumably the address where the X is stored. This is the address where the G is stored. What else? Anything else that you see here that's interesting? They're all. Yeah, I don't know what this means. Yeah, I don't actually know what this means either, nor do I know what that means. I only know what a few of these things are. So yeah, somebody said something about the two X's. Well, that's interesting. Here I've got two X's. You'll notice this is the same address as this. So R seems to be smart enough that if it has duplicates, it can just point to, so the fifth thing was another X, and it just points over to the same X that the first one pointed to. So that's kind of cool and kind of clever that it does that. Okay, so I don't actually want to go really any further into how character strings are stored. I just wanted to sort of use this as a little bit of, just to get a sense for it. Yeah, quick question?
have a mixed ASCII Unicode string?
I think it's probably going to interpret that as fully Unicode, and the ASCII characters are just a subset of them. Okay, so we'll stop there, and next time we'll start talking about how real numbers, decimals, are interpreted on a computer and what the implications of that are.